So now we have done the miraculous. We have determined the acceleration of Earth's gravity at the surface using a rock, a string, a yardstick, and a wristwatch. And we've determined that the acceleration of gravity is 9.843 meters per second squared. That's pretty close to 9.8. What do you know? Physics works. This goes to our simplified or hacked version of Newton's law of gravity. And using a little bit of algebraic razzle-dazzle, we can rewrite that so that it reads m equals Fg r squared over g, the gravitational constant. So we should be able to plug in some numbers and figure out what the mass of the Earth is. What we need to know is the radius of the Earth. Well, the Greeks figured that one out over 2,000 years ago. And we've refined it since then, obviously. The radius of the Earth, and that's a symbol for the Earth, is 6,378 kilometers. But we're going to have to convert that into scientific notation, and we're going to have to turn it into meters. So kilo is 10 to the third, and we bump it over 3 places to the left. 1, 2, 3, and we get 6.378 times 10 to the 6th meters. So now we have all our pieces and parts. The only thing we need to do now is just plug them into the formula. So here we go. M will equal force of gravity, which is numerically, in this case, this is our cheat, is going to be equal to our acceleration numerically. So we're going to plug in 9.843 times the square of the radius, 6.378 times 10 to the 6th all squared over the universal gravitational constant, 6.672 times 10 to the negative 11. Now it's just a matter of bashing out the numbers. First I'll square this. 6.378 squared. That comes out to 40.679. 10 to the 6th times and squared comes out to the 12th over 6.672 times 10 to the negative 11. Now I'll multiply these. 9.843 times 40.679. And I get 400.403. Times 10 to the 12th over 6.672 times 10 to the negative 11. Now I'll divide. I get 60.012 times 10 to the negative 23, which becomes 6.001 times 10, oh that's a positive 23, times 10 to the 24th kilograms. And that's a little bit high, but we would expect that because our gravity was just a little bit high. So that would be consistent with our original number. So there you go. It's as simple as that. Now we know the mass of the Earth. And from there, we can determine, if we wanted, we could use that data to calculate the period of a lunar orbit using, wait for it, Newton's version of Kepler's third law. Stuff we've already done. Okay, so just for grins, we'll go ahead and do that. So we're going to hang on to this figure here. .001 times 10 to the 24th kilograms. We'll leave this up here. So, how do we do that? Well, we use Newton's version of Kepler's third law, which states that the square of the period is equal to 4 times pi squared times the cube of the orbital radius divided by the gravitational constant and the mass of the planet. So again, just a matter of plugging in numbers. So, p squared equals 4 times 3.14 times the radius. Oh, we need to know what the orbital radius is. Well, the orbital radius of, the average orbital radius of the moon is 384,000 kilometers. And we'll turn that into scientific notation in meters. So kilo is 10 to the third, and then we're going to go 1, 2, 3, 4, 5 to the left. That's going to make it 3.84 times 10 to the 8th meters. All right, so that's our orbital radius. And so here we go, 3.84 times 10 to the 8th cubed over G, 6.672 times 10 to the negative 11 times our mass, which we figured was 6.001 times 10 to the 24th. Okay, all we gotta do now is bash out numbers. Oh, this is supposed to be squared. I forgot to put that there. Okay, so I'll start by squaring pi. 3.14 squared equals 9.8596. I'm going to multiply that times 4. And I get 39.438. And now I'll cube this number, 3.84 cubed. 3.84 cubed. 56.623 times 10 to the 24th. I'll multiply these. 6.672 times 6.001. 40.039. Times 10, 24 minus 11, that would be 10 to the 13th. Okay, we'll multiply these. So 39.438 times 56.623, 2233.098. times 10 to the 24th over 40.039 times 10 to the 13th. So now I'll divide this by this. And I get 55.773. Okay. Times 10 to the 11th. Okay. All right, now, remember, this is p squared. So that's what p squared is. And we don't want p squared, we want p. So how do you unsquare something? Well, you square root it. So p is going to equal the square root of 55.773 times 10 to the 11th. Okay, well, can't do a square root of on an odd numbered exponent, so we're going to cheat. I'm going to raise it up to 10 to the 12th. That will make it 5.577 times 10 to the 12th. All right, so now square root. 5.577. I got 2.362. Divided by 2 times 10 to the 6 seconds. So that's the period of one lunar orbit. Now, that doesn't make a lot of sense to me, so I'm going to convert that into days. So I'll set up my conversion. 2.362 times 10 to the 6 seconds over 1. And now cross cancel seconds and replace seconds with hours. And then I'll set up to cross cancel hours. And replace hours with days. 3.6 times 10 to the 3rd seconds makes 1 hour. 2.4 times 10 to the 1st hours makes 1 day. Now I can cross cancel. Cross cancel my seconds, my hours. Okay. Now, I can cross cancel my powers of 10 here too. 10 to the 3rd times 10 to the 1st is 10 to the 4th. 10 to the 6th over 10 to the 4th, that becomes 10 squared. So now I'll rewrite it. 2.362 times 10 squared days over 3.6 times 2.4. 3.6 times 2.4, 8.64. So 2.362 .362 divided by 8.64, I get 0.273 times 10 squared days. Or if I want to put that in standard notation, that's going to equal 27.33 days. And that comes out to be just a little bit shorter than what the lunar orbit period actually is. And if you think about it, that makes sense. Recall that we determined through our experiment using the pendulum that the gravity was a little bit higher than 9.8, which would mean that there was more mass. If there's more mass, there's more gravity. That means that the moon's getting a stronger pull toward the Earth. All right, so it's going to have to go a little bit faster to prevent that from happening. And if it goes a little bit faster, then the period is going to be a little bit shorter. And there it is. Oh, right there, sorry. There it is. So, there it is. We started with a rock and a string, and we finished up by calculating a lunar period. Now, the thing that is amazing to me, but I'm a nerd, is how the way that rock on the end of the string is directly related to what we see in the sky 2 weeks out of 4 when we watch that moon go around. This is what Newton figured out. This is the genius of Newton. He saw that those two seemingly separate phenomena are actually directly linked to one another. That's pretty fantastic, I think. But then again, I'm a nerd.